Hello everyone, welcome to my civil engineering YouTube channel. Please subscribe to it and hit the bell icon to get notified when I post my new videos. So today I'll be discussing one more numerical on stress strain and Young's modulus concept. So I have taken a numerical as a wood tie which is 75 mm wide, 150 mm deep and 1.5 meter long. So this is a wooden tie wherein it is having the dimensions of length equal to 1.5 meter, width equal to 75 mm, and depth is equal to 150 mm. So it is then subjected to axial pull of 45,000 Newton, or it is also taken as 45 kilonewton. So here they have given stretch of the member is found to be 0.6380 mm. So they have asked to find the Young's modulus for the material. So basically here they have given a wooden object wherein the dimensions of the wooden object is having the length of 1.5 meter, width as 75 mm, depth as 150 mm. So here they have also given that wooden object is subjected to the axial pull. So it is subjected to axial pull. Pull means here it is subjected to a tensile force. So it is subjected to tensile force of 45 kilonewton or 45,000 Newton, wherein so as soon as there is a object, when it is subjected to the tensile load, it will be subjected to extension. So therefore the extension or stretch in the member is found to be 0.6380 mm. So here they are asking to find the Young's modulus for the material. So first and foremost step is as I said, that the extraction of data from the question. So here the first thing is the width given. Width of the wooden tie, it is 75 mm. Depth here is given as 150 mm, and then length here as 1.5 meter. So since both the dimensions here is in mm, so we can convert that length in meter in terms of mm. So 1.5 multiplied by 10 power 3, so it is 1.5 into 10 power 3 mm. So load they have given as 45,000 Newton, and stretch, that is elongation, stretch or elongation, it is equal to 0.6380 mm. So here they are asking asking to find out what is the modulus of elasticity or Young's modulus of the material. So the next step is calculation of the area of the material. So here, since it is given as a material with the geometrical shape as rectangle, because you can just identify length, width and depth is given. So since length, width and depth is given, so it is nothing but a rectangular dimension. So area of the material will be B into D here. So why it is B into D here means, so why I have not taken L into B or L into D? Only I have taken here as B into D. Why? Because so since I have applied the load along the length, I have applied the load. So if at all, if I am going to apply the load along the length, so apart from that dimension wherein the load is applied, apart from that dimension, I need to take the other two dimensions. So here, therefore, I am going to take the B into D as the area of material. So suppose if the material is subjected to the axial pull along the width. So in the question, if the question it is mentioned as along the width, the force is subjected. So then the area will be equal to L into D in such case. So like that. So here in the question they have mentioned as it is subjected to axial pull. So axial pull means always it is understood that it is the object wherein the load is applied along the length itself, so therefore the area will be equal to B into D. So here B is equal to 75, D is equal to 150. Substitute that and get the value of area. It is equal to 11.25 into 10 power 3 mm square. So this is the area of cross section of the material when it is subjected to the axial pull. So next step is calculation of intensity of stress. So intensity of stress. So here they have asked to find out the Young's modulus. So as you know that the Young's modulus is nothing but the ratio of stress to strain. So we need to find out what is stress, strain, and substituting that stress and strain we need to calculate the Young's modulus. So therefore I am going to find out the intensity of the stress here. So stress, I know that it is load by cross sectional area. So load they have given as 45,000 Newton, and cross sectional area just we have found out by in the previous step. So that is 11.25 into 10 power 3. So substituting that I'll get the stress in terms of Newton per mm square. Why? Because the load I have substituted in terms of Newton and cross sectional area in terms of mm square. So therefore it will be in terms of Newton per mm square. So therefore after substituting that and simplifying that, I'll get the stress as 4 Newton per mm square. So next, calculation of the strain. So here the strain is nothing but ratio of change in dimension to the original dimension. So general formula is ratio of change in dimension to the original dimension. So in this problem in particular, change in dimension is nothing but the elongation and original dimension is nothing but the original length. So original dimension is length. It is given as actually it is 150. So length, it should be 150, the length 1.5 into 10 power 3. So length they have given as 1.5 into 10 power 3. So length they have given. So stretch they have given as 0.6380 they have given the stretch. So 0.6380 divided by 1.5 into 10 power 3. So if I do that, I'll get the strain as 0.7 into 10 power 3. So 0.7 into 10 power minus 3. Sorry, 0.7 into 10 power minus 3. So here there is no units because the ratio is between the same units. So strain will not have any units. So it is 0.7 into 10 power minus 3. So next step is calculation of Young's modulus here. So I know the stress and also the strain in the step 3 and step 4 I have calculated it. So after the calculation, just I need to substitute what is the values for stress and strain in order to calculate the Young's modulus. So therefore I know what is Young's modulus, that is nothing but ratio of sigma by E. Sigma is the stress and E is the strain. So 4 divided by 0.7 into 10 power minus 3. So I'll get the Young's modulus as 5.71 into 10 power 3 Newton per mm square. So this is what the finding of Young's modulus by using stress and strain. Thank you for watching. Please like, share and subscribe the video. Thank you.